Welcome to this episode of the Structural Engineering Channel, a podcast focused on helping structural engineering professionals stay up to date on technical trends in the field and to help them succeed in their careers and lives. The Baltimore Bridge collapse has been a hot topic for the past couple months, and today Rachel and I are going to be speaking with Roberto Leon, Ph.D., and he's the professor of civil and environmental engineering at Virginia Tech, about the aftermath of the Baltimore Bridge collapse, including what the future holds for its reconstruction and the broader implications for infrastructure resilience. I'm your co-host, Matt Picardle.
And I'm your co-host, Rachel Holland. Now let's jump into the conversation of the week.
Roberto, thanks so much for joining us. Can you tell us by starting to tell us what you do on a daily basis?
Sure. So I'm a college professor, so I do basically three things. One is teaching, and so I teach mostly structural design, both at the undergraduate and graduate level, and I teach a class, which I just finished teaching this past semester, on what is called forensic engineering, which is failure analysis. And so one of the reasons I'm interested in the collapse of the Baltimore Bridge is that. I also do research, and I've spent my career doing mostly large-scale experimentation, testing in the laboratory, large pieces of structures, mostly for seismic forces, for earthquakes. And finally, the third component is called service, which means that I work with professional societies. And so, for example, I serve on technical committees. I sit on the committee that writes the steel building specification for the United States.
Awesome. I know we're going to focus on the Baltimore Bridge for this podcast episode, but I always love hearing how people got into education. So maybe that is a future conversation.
Sure.
But for our listeners for today, who maybe are not as familiar with the Baltimore Bridge collapse, can you give an overview of that incident and maybe just touch on the immediate consequences of that collapse in terms of both the infrastructure and how it impacted the community?
Yes, on the night of March 26th, a container ship named the Dali, registered in Singapore, left the port of Baltimore. When ships are moved from the berth, they're generally moved by tugs, and so two tugs pulled the ship into the main channel to get out of the port, let go of the ship, and the ship started moving towards the open sea. However, very soon after that, they lost all power, which meant that they had absolutely no control over the ship, particularly the rudders, the ability to turn the ship. Briefly after that, they recovered some of the power, but they were unable to do very much. And so the ship basically continued at its velocity, which was about 8 knots, and hit the southern support of the Key Bridge, and the bridge collapsed, and part of the bridge collapsed on top of the ship, which meant that the ship was basically trapped there. And some of your readers or listeners, I should say, should have seen the explosions that they did this past Tuesday to remove some of those remains from the top of the ship. So basically, we lost a very important communication channel around the city of Baltimore, which meant that, first of all, people were impacted and businesses were impacted because they had to either close or reduce operations or travel far more. And most importantly, the debris from the bridge blocked the Port of Baltimore, which is one of the major ports in the eastern United States, particularly dealing with cars and moving cars in and out of the U.S. So just a huge impact. I have not seen estimates, but it is possible that losses are in the millions of dollars per day when you account for direct and indirect losses.
How long did the port stay blocked? Is it still blocked?
The port reopened at a reduced rate about 3 weeks ago. All the ships that had been caught inside have left now, and traffic is not quite back to normal. But I would say, except for the biggest ships, most of them are able to go in and out now. Obviously, they are being escorted by tugs because the the channel is much narrower than it needs to be.
Yeah, the financial impacts on that, even the long term, if a port is shut down due to traffic, I'm sure the ship's got to go someplace else, and hopefully they return back to get the economy going. But things like that, really unfortunate, not including all the traffic that used to go over the bridge. I can imagine what the impacts on that.
If I can, I can give you an example of what happened to the port of Kobe in Japan after the 1995 earthquake.
Oh, yeah, sure.
At that point, Kobe was an enormous port, the fourth largest port in the East, and it was heavily damaged by the earthquake. And the Japanese government made a priority of opening it up, and it was opened within, I believe, 12 months or so. However, by then, all the shipping had moved someplace else, and today Kobe is probably the number 35 or 40 port in the East. So one of the things that you learn on these disasters is that people are going to, because our just-in-time chain of distribution requires that things keep moving. People are going to move and they're not going to come back. So it's going to be interesting to see the long-term impacts on the city of Baltimore. Hopefully not too bad, but they could be substantial.
Wow. Yeah, from 4th to 35, and then they couldn't recover. Interesting. Yeah.
Right.
Yeah.
And with regards to the bridge, were there any design flaws with it structurally, or was it just a freak accident?
It was just a freak accident. The bridge was well designed for its time. And the bridge was actually in very good shape. The what we call the superstructure, which is the upper portion, the truss that you see there, that was rated an 8, I think. And the substructure, which is the piers and the foundations, were rated a 6. For a bridge of that age, those were very good ratings. So the bridge was in very good shape. However, it was not well protected, and it is hard to say, even if there had been some substantial protection, if it would have been able to resist this ship. The ship was loaded, I think, at about 5,600 containers, which is not a lot, but the total dead weight of the ship and the containers, I've read some places, about 110,000 tons. And moving at that speed, which was about a little less than 10 miles an hour, there's nothing that's going to stop that without some very serious damage, which is what happened here. So again, the bridge itself, if you had asked me what is going to happen to this bridge should it get hit by this size ship at that speed, I would have said it would have gone down. The issue is that when we design any piece of infrastructure, right, we are looking for a very low probability of failure. But at some point, buying extra safety starts costing way too much money. And so in structural design, we're sort of getting or trying to hit that sweet spot where, you have gained a lot of safety, but it is not extra cost.
Right.
And so that's a compromise that we always make. And one that unfortunately the public, I don't think really appreciates. They don't appreciate that there is always a probability of failure. For example, the AASHTO specification, the American Association for State Highway and Transportation Officials bridge specification, for this kind of event assumes a failure probability of about 1 in 10,000. And you might decide, oh, that sounds pretty good or not so good.
So for this, well, I mean, like you're saying, it was such a heavy ship moving at that speed, probably not a lot that could have been done to prevent that collapse. But are there any measures that you can think of that could have helped to protect the bridge from a collision? Like you're saying, for AASHTO, it's a 1 in 10,000 that the code says to build to.
Right.
Like, do sometimes people decide to go more conservative?
More than that,
I mean,
yes.
how does that work?
Every building code represents a minimum, okay? And so in many situations, engineers will tell their clients, I can do so much better a job by, that is going to cost you only 2 or 3% more, okay? And so one has to be careful with assuming that first of all, that the codes are perfect, right? The other thing that's important here, right, is the ship size has changed so much since this bridge was designed that even if it had been designed to sustain impacts from heavy ships, it wouldn't have mattered very much at all. So there are a number of things that we can do to protect a bridge of this type. That's being done on lots of bridges. Your listeners can go and look, for example, at the pictures of the bridge over Tampa Bay, the Sunshine Skyway Bridge. That was hit and collapsed by a similar accident in the early 1980s, if I recall. And when it was rebuilt with a bridge very similar to the one that's probably going to go into Baltimore, a cable-stayed bridge. But if you look around the base of the bridge, you will see very large so-called dolphins. These are very large protective structures. Don't ask me where the term dolphin comes from, because nobody knows, apparently, but they're called dolphins. And so you could put a lot of those. And one of the interesting things about this Sunshine Skyway Bridge is that they are not protecting only the main span of the bridge, but also the approach spans. Because think, the main span could have been fine, but if they had taken out the approaches, we'd still be in the same pickle to some degree. Maybe not as big an issue, but it could have happened.
So for this bridge in particular, when was it built, and how long ago in the code cycle?
It's almost 50 years old.
Okay, so it's been a while.
So it's what we call a through truss. Is a very efficient design. Is not what some people would call the prettiest of design. But it's a very efficient truss bridge capable of carrying the loads with a minimum amount of material. And one of the things that one needs to appreciate is that we do that because, in general, the cost of the foundations on a bridge is the most important cost, or sometimes is the most important cost, just depending on the local geology and soil conditions. So if you can reduce the weight of the bridge, then your foundations are smaller, they're easier to do, and so that saves a lot of money. So one of the rationales for those types of bridges was that they were very light and again, met all the design requirements. But it's interesting, just to bring another topic here, right? When this bridge was designed, the whole eastern portion of the United States was not considered to be a seismic zone. A few weeks ago, we had a little earthquake in New Jersey, right, which is entirely, I would say, in accordance to the seismic risk that we expect for that area. But when this new bridge gets redesigned, okay, there is going to be a very large horizontal component that the bridge is going to have to be able to resist because of the earthquake forces. And so, and again, we have newer provisions for vessel collisions. So the piers for this bridge will be pretty massive. But also, we are probably going to have a much longer span. So the piers are going to be way out of the navigation channel. And I think that's where we're going to end up, with a much larger central span and the piers well away from the navigation channel. But that does pose another design problem, which means that the bridge is going to be very high from very far out. So the approaches, how you're going to build the approaches is going to be a pretty important component. So this is going to lead not just to a redesign of the bridge, but the entire area on the approaches of the bridge is going to have to be redesigned and repurposed.
Interesting. Just another follow-up question to that. You said the bridge is at least probably about 50 years old. I'm curious, do you know if today's standard is that 1 in 10,000 chance of it being hit by a ship? What was it back then? Do you know?
There was not a number. And so we have begun to put numbers to these in the last 25 to 30 years, when we have begun to do probabilistic analysis and reliability analysis.
Got it.
And so let me cite as an aside, another number that your listeners might be interested in. If we design a building today, a new building, and it complies with all of our most modern seismic design requirements, if what we call the maximum credible earthquake were to occur, some recent studies show that a brand new building might have up to a 10% probability of collapse. Okay? If you tell that to people, most of them will say, that's unacceptable. You know, we paid a lot of money for the design, but it is that same sort of compromise that I was talking about before, right? So your probability of having the maximum credible earthquake is roughly a return period of 2,475 years. So, you know, we're playing with probabilities all day, you know, and so and these are random events. Yeah. I'll tell you, for example, I worked for many years at the University of Minnesota in Minneapolis. I drove over the I-35 W bridge that collapsed in 2007, I don't know how many times, in the thousands probably, because it's right next to the university. So I used to drive over it to get to the university. And, you know, I never thought it was going to collapse, right? It never even occurred to me. I actually worked on that bridge or did some inspections on a completely unrelated thing many years before it collapsed. And so I had no reason to distrust the bridge, put it that way.
Yeah, I think that's something that the public probably doesn't appreciate too much in terms of the way we design things. It's probabilities, and whether it's good enough or good. I mean, you got to take into account the economies, like you were saying earlier. Like, yeah, we can, but no one's going to be able to build it.
Right, and one of the issues that needs to be sort of highlighted here is that the what we call the probability distributions that we use in this kind of events, which are very rare, are not sort of the normal distributions that people are used to from high school probability classes or math classes. They are what we call long tail distributions. So they you know, in order to reduce what it means practically is that in order to reduce the probabilities of failure, you have to go way out in the probability distribution, and so that's what becomes so costly. And so, you know, again, I think that engineers designed to specifications that are, you know, very up to date, very reasonable, but they don't guarantee anything. You know, as again, people sort of take building codes as you know, infallible. They're not.
Do you see any lessons or maybe changes to bridge design that the bridge industry will learn when they're doing these types of bridges? I think you mentioned a few for that particular bridge, but what about in general?
So I think, first of all, you know, Chapter 3, Section 14 of the bridge specification is going to change significantly. That's the one on vessel collision. It will be updated. It is in the framework that is there is fine, but I think a lot of details are going to need to change. And so that's one part. But I think what's most important here, and a number of these disasters bring it forth, is that when we are planning for, let's say, new structures of this size, people need to take ownership and ask questions. The public, there are always public hearings when major projects like this occur, right? And so the public needs to ask, so what are these compromises? Okay, tell me a little bit. You know, sometimes it's not easy for an engineer to explain that, but the public needs to understand that if they are paying taxes and their taxes are going towards these projects, right, which is the case here because apparently everything is going to be paid by federal money. So everybody in the country has an interest in this, right? Then we should be asking the questions, what am I buying for this, right? And if it is this bridge, is probably going to cost, at least initially, the initial estimate is somewhere between $1.7 and $2 billion. By the time it gets done, it's probably going to be a lot more than that. That's our experience with any project, okay? Because we don't know everything that's in the future. And so, just cost of materials, for example, it's a huge issue right now. So it is hard to predict how much is going to cost. But let's say if 100 million buys you a heck of a lot more, why not go for the 100 million, right? And so the public needs to appreciate that it's not a matter of going for the cheapest product, even if the cheapest product meets all the minimum requirements. People should appreciate it, and you do it when you buy a home, right? There are lots of things about your home that you don't need, but you say, oh, there's a large recreation room, or there's a jacuzzi, and there are all of these extra things, right? And you're willing to pay for those. Why aren't you willing to pay for those for a bridge or a piece of infrastructure? And by the way, this applies not just to bridges. This applies to things like water treatment plants, electrical transmission towers, any piece of infrastructure that you want to talk about. People should become a little more knowledgeable and ask questions.
I will say, though, 1% of like a multi-billion-dollar project is a little different than, 1% on your single-family home. That number can be a little daunting. But yeah, I understand what you're saying.
You are perfectly right. So that's the problem is, if I say, it's going to cost you another $5,000 for all of these things in your home, but I say it's $500 million on something else.
It feels different.
You're right. But people need to understand also, what is their share of that bridge? In other words, you paid, I don't know, $20,000 in taxes this year. How much is going into that? Right. It's a very small amount.
Yes.
And so, again, it's an issue that we need to perhaps be a little more conscious of what I've called in some instances community resilience. Being community resilience really means preparing for a disaster, doing whatever you can do to mitigate, but also planning as to what's going to happen should a disaster occur and how you're able to recover from that disaster. And so, your listeners can think about the Katrina disaster, right? And how some parts of New Orleans came back, to what they were before. And there are other places that are a complete disaster today.
Yeah.
And so that's the concept of resilience. How do we get back? Right? And how do we plan for all of that? How do we build resilience into our structures? To give you an idea, for example, I said that the new bridge is going to be a cable stayed structure. Okay, and so you're familiar with these cables that come down, right? It is very easy and routinely done today. That the bridge is designed so those cables can be replaced if they are damaged. And you don't even have to put the bridge out of service for very long. It's a very simple operation because from the word go, that was considered to be a design requirement. And so that kind of thing is what I'm talking about. There are lots of things that can be done to even improve maintenance or make maintenance easier. That's the kind of thing that I'm talking about.
Yeah. I think like one of the things that's really important is like being on like the engineering side of it or the development side of it, the building side of it. We're more educated on why those certain improvements are necessary. So, I mean, like so much in so many aspects of the world, but it's like the people that really understand it need to be educating the taxpayers as to why that little bump makes a difference, because I think just as like a consumer or like a community member, if that's not your area of expertise, like you just sort of go around. I mean, it's like our human nature. We just expect it to work. We don't really think anything of it. We expect that building to stay standing. We expect that bridge to be safe to drive over. Otherwise, why would the world let us drive over it,
So, Rachel, let me make a point about what you're saying. So one of the things that we are emphasizing a lot nowadays in education is communications, both written and oral communications, because that's really what engineers need to be able to do, to communicate these things to their clients and to the public. And very often we don't do a good job of doing that. And the other thing is that we don't have enough engineers that are involved in politics. I routinely ask, and I will not give the answer, but your listeners can guess at how many members of Congress are engineers. Okay, between senators and representatives, and compare that to the number of lawyers. Now that's an unfair comparison, but let's just say. Right. And, interestingly enough, there are also 2 U.S. presidents that have been engineers. And can you name them?
I can't. I should know this, though. Matt, we should know this.
Yeah.
Who are they?
See, I put you on the spot.
Yeah, who are they?
Carter.
Okay.
And, the one that came right before the Great Depression.
Hoover. Okay.
Neither of them has left a most positive impression. Although, by the way, I greatly admire and I love Jimmy Carter. I think he was just the wrong person at the wrong time and the wrong place.
So is it safe to say, though, people like when they're younger and they're starting out in like their educational selections and things like that, I would say people that are interested in engineering are not necessarily the same type of person that aspire to be a politician. So
correct, but we need to attract those people to engineering. And so again, for us, an interesting additional issue is that, the demographics indicate that the number of students are going to keep coming down in the future. And for the engineering industry as a whole, that means that if we keep growing, which we are in almost all areas, we need a larger percentage of the students going into engineering. And how do we recruit that? Engineering has a reputation for being difficult, and it has to be, because the problems we are dealing with today are so complex. It's interesting for me to just think about when I started and what issues are today, and just the degree of complexity is enormous. I was reading on the report from the Baltimore Bridge that came out this past Tuesday regarding the electrical system and what could have gone wrong there. And, the report doesn't say anything about the cause, but it just begins to sketch how complex that system was, right? And those systems are run by computer programs. And nobody that I know is able to tell you, we tested every possible, path in that system to make sure that it was, 100% correct. It's just too difficult. And I would not be surprised if that's what lays at the bottom of what happened in Baltimore.
What about, I'm going to jump here. A minute ago, you talked about how the proposed replacement for that bridge is a cable-stayed bridge. And you talked about how it's a preferred one because how you can just replace a single cable when necessary and things like that. Are there any other aesthetic or functional benefits that type of bridge offers that's like one of the more of the reasons that they're going to go with that style?
Yes, there are many. Again, primarily because the span that is desired, the economics almost dictate, I think, at this point, a cable-stayed bridge. But one of the issues or one of the advantages of cable-stayed bridges, depending on how you build them, is that a lot of it can be prefabricated. For example, large pieces of the deck can be prefabricated, put on a barge, and then just lifted into place. So it minimizes all the construction on site, which is the most expensive and most time-consuming part of the operation. Obviously, again, they can be tailored to almost any span, and there will be very different designs. I think there's still going to be a cable-stayed one, but there may be interesting competing designs. The span is such that a suspension bridge. This is too short for a suspension bridge. Is too far now for a truss bridge, and truss bridges are not considered to be very aesthetically pleasing, and a lot of the cable stayed bridges are that. Again, the city of Baltimore is probably looking for a signature bridge, similar, for example, to the so-called self-anchored suspension bridge that was built on the Oakland-San Francisco crossing not too long ago. I don't know if you have that in mind, but it's quite an interesting structure from the engineering side, but it's one that people have really adopted.
I live in the Bay Area.
It's really interesting.
I go over that one a lot.
Huh? But to me, it's interesting because that bridge started costing the cheap alternative to that bridge in the early 90s was about $450 million, which was just a concrete box girder bridge. And we ended up upwards of $15 billion.
Wow.
Right? Okay. Now, the interesting thing to me, though, is my children live in the Bay Area, so I go there a lot. And I think the people in San Francisco and Oakland are really pleased with that bridge. They don't care that they're paying more for it, right, in terms of tolls. Initially, there was a big brouhaha about the whole thing, and now people have adopted the bridge. The bridge is their bridge, particularly on the Oakland side, right, because San Francisco has the Golden Gate. But so those are sort of the things that it is very hard to put a value on. So, there might be some interesting designs coming up. One of the people that might get involved, I don't know if he will, is Santiago Calatrava, the Spanish engineer that does some beautiful but very expensive and problematic bridges.
I've seen some of those.
He gets sued in every project that he does, right? But anyway, so no, I think aesthetically, the cable stayed bridge is a great alternative. And again, because there are lots of possibilities.
Right.
And I'm guessing they're wanting to build this bridge and design it as soon as possible. I'm guessing with an accelerated timeline. How long do you think that is? And are there any issues with the accelerated timeline?
So about a week and a half ago, the Maryland Department of Transportation had a sort of get-together for everybody that was interested in this bridge, and they indicated that they would have an RFP for the bridge before the end of May, and that was for the whole design portion, and that could be up to about $500 million. And that they wanted that done as soon as possible so they could go on with the second portion, which is the construction. And the way this contract is set up is what they call a progressive design build. So the company that wins the design, has priority on the second contract, which is the construction. If the firm that wins the first contract is able to, get an agreement with the state about the cost of the second part, the construction, which is the biggest one, that will happen automatically. There will not be a second round of bids for that. And that's in order to speed up the whole process. The whole thing there, they speculated that if everything goes well, the new bridge will open in the fall or early winter of 28. So that's 4 years from now. Now, I have thought that there are ways of building something using what we call accelerated bridge construction. So that's ABC is the terminology there, that could help speed things up. But again, the design of a bridge of this size is not trivial. I know, the major bridge firms were working on the redesign the day after the accident. They started working there. So, they're going to have basically probably less than 30 days to respond to that initial RFP. But most of them already have some sort of design. A couple of them have actually been published. The one from a company called Rebuild, which is a large Italian company. It used to be called Imprelio. They have built bridges all around the world, impressive bridges. So, and they're bringing in probably the best bridge designer in Europe at this point as their chief technical person. They already have a design, and they have posted everything out there. You can go and look at their design. Again, the company's called Rebuild, but all the American big companies are working on that, and all of them are going to bid.
So obviously,
it's too big a project not to for a reputable bridge firm not to try to go after.
Yeah,
it.
Totally. So obviously, timeline is like a big consideration in this, but also you mentioned earlier the cost. They're estimating that to be in the billions, and when you're dealing with a large scale infrastructure project like this, how do uncertainties in like foundational costs and different things like that impact the budgeting and the planning? And then I guess as the follow through for that, it's going to affect the timeline, right?
So I don't, since the RFP hasn't come out, I have no idea what the specifics are here. But obviously there are always very large contingencies in a project of this type. And as you know, then everything is a change order from there on. And so that's why when I said, well, they're talking about $1.7 to $2 billion, but then the change orders come. Now, in this particular case, I'm not sure, but a lot of the unknowns that are going to cost money are the foundations. And so I am assuming that we have a pretty good idea of the geology of this site and of the type of rock and the types of soils. So it might, from the word go, there's probably a little bit more information than if you were starting on a new site from nothing, right, from scratch. And other things that usually take a lot of time are environmental permits. And so in this particular case, I think, somebody speculated that they should just rebuild the old bridge, because if they did that, they need not do anything with environmental impact statements, which I'm not sure if that's right or not, but it was just an interesting take, right? Because in any of these projects, you have water underneath, right? It's a big issue. Just to give you an example, again, going back to the Oakland-San Francisco Bay Bridge, when they finished the new bridge, right, the older truss bridge that was on the side was basically taken apart like a tinker toy, with every last piece being brought back to Oakland through the existing roadway. They were basically taking the bridge apart piece by piece because California would not allow them to drop a piece of steel or a bolt into the Bay Area for environmental reasons. And they did it. Actually, to me, that's almost as interesting and challenging a project as building the new bridge was, because the stability there was a huge issue. I don't know, Rachel, you mentioned that you drive over it, but a couple of times I'm driving, I'm looking over there, I'm saying, that thing doesn't look right.
Yeah, it would just be like a piece still hanging there that you're like, they must be taking that down next. But it would have been better if they did that at the same time.
Right.
Yeah.
And Roberto, you mentioned earlier, about if the public knew more about it, maybe they might add more money to it to better protect it. If they knew, like, oh yeah, we want a bridge that's better protected. What type of things could they do to add more protection to the bridge if they threw more money at it?
Well, one of the things that is incumbent on people like myself, who are researchers, is to come up with a better mousetrap. We have dolphins, we have islands. Are there other things? And so some of us that work on the seismic side of design are very interested in what are called energy absorption and isolators and things of that sort, newer technologies. Newer materials, for example, there are things such as metallic foams that are used in the automobile industry, right? You see automobiles nowadays completely crumple up to the passenger cabin, right? And they absorb all the energy, right? Well, we need to be thinking the same way, right? And we need to be thinking that these are what we call sacrificial elements, right? Because this is such a rare event. Should it happen, we're going to have to replace the protective system. It doesn't matter, right? Because the cost will be only, let's say, speculate, $100 million, right, to replace that, right? But the bridge is fine. You have no 4 years without a bridge. You didn't have all the economic losses and so on. And so it's clearly a good trade-off, right? It's buying insurance, basically. So I think that there's going to be a lot that's going to change there. Yet I think that primarily FHWA and AASHTO and the local Department of Transportation are going to start asking themselves, should I pay a little more with a bridge that has to span more, but I'm now buying safety because the channel is such that there's no way a large ship will ever get to where my piers are. That's what they're thinking, right? Now, ships will do their own thing, and maybe that's not a sure thing, but that's the kind of thinking that we need to get out there, and the public needs to insist on that, right? Just like they insist on maintaining wetlands, right? We don't need to destroy the wetlands to build a bridge nowadays. We know how to do it. It does cost more, but we are willing to pay for that, right? And so I think it's just better informing people of what the choices are. And again, participation, for example, again, going back to I know a lot about the Oakland-San Francisco Bay Bridge because I did a review once for that project. And so the reason it went from a $450 million bridge to a $15 billion bridge was because the public decided the concrete alternative is the ugliest thing in the world. We want a signature bridge. And from there, it just escalated. Okay? And you could argue that they went too far. But again, I think that's the model. And you know, one thing that I think is important here is that minorities and poorer people are not often taken into account in these designs. And you know, again, I was talking about the changes in the approaches and so on. You know, if we go back to when we first put the interstate highway system into our cities, right? We did a lot of damage to some of the minority communities. Baltimore is actually a good example of that. So, you know, taking a little bit of social justice into account in the designs is something that we really need to do. And it is incumbent upon us, the engineers, to actually do that, right? And so I'm heartened because a lot of our undergraduate students take that to heart nowadays. It's relatively new concept, but
I feel like it's talked about more now. Getting a little bit more back into like the community and then also just like community resilience. I'm curious, you mentioned that the estimate is for summer or fall of 2028 for that new one to reopen. So that's a solid 4 years, assuming it stays on track, which construction projects, we all know. So how, and then like with the Kobe one where it fell from like the third port to the 35th or whatever. How do you know, like in comparison, how long did it take to rebuild that one versus how long it's going to take to rebuild this one?
It was about a year because what happened in Kobe is a lot of the port was built on landfills and they had a lot of liquefaction.
Okay.
And so for example, all their container cranes went off the rails and, you know, the surface was very uneven. They had to do that. So I'm not anticipating because the port of Baltimore essentially was closed probably for about a month. it is a completely different thing, I think.
But what about like in terms of, okay, so maybe it's not a good comparison of the two for this aspect of it, but being like having the bridge closed for 4 years in terms of people like getting over it, going to their jobs,
Right.
like doing all the things you have to do on the other side of the bridge, like how, like just in regards to this incident and like what's going to happen?
I mean, what's going to happen, I think, is that people on either side of the bridge are going to find alternatives to what they used to go across. So when the new bridge shows up, there is little incentive for them to, 4 years later, change their relationship with a business, right? 4 years is a long time. That's, I think, what you're talking about. And so I don't think that that kind of traffic is going to be there anymore.
Or at least not initially.
Now,
but maybe, when it gets rebuilt, that'll
right.
open up options. So maybe it'll just grow slowly again.
Right.
Okay.
Again, a better analogy that I'm familiar with, I was in Christchurch, New Zealand, when the big earthquake occurred in 2011. And this was a British-type city which had what they call a central business district. So there was an area about a mile by a mile in the center of Christchurch where everything was. And that got wiped out. And nobody could even go in there for about a year. You couldn't even go and retrieve stuff. Okay? And so all of these businesses moved to the outskirts. And for the past 10 years, Christchurch has been trying to attract those businesses back. And it's not happening. It's just not happening because, again, people move, they establish new relationships, they find new sources for what they need to do, and you find no reason to go back to what was there before. In fact, these are opportunities for a lot of people to change the way they do business and to modernize the way they do businesses because they're kind of starting not necessarily from scratch, but they can make leaps in technologies, for example. And so the event is very disruptive. But one of the interesting things is it will be to see what new things happen, right? Because obviously we can't expect to keep things going like they were before. People are, from the north end are not going to drive to the south end to pick up I don't know, or to go to a hairdresser or something like that.
Yeah.
Right? Or to find their favorite restaurant. Maybe, every once in a while a restaurant you might do that, but on an everyday basis that's not going to happen. And so I think that some of the people who have the most interest here are sociologists to look at that. I'm not sure if you're familiar with I forget her first name. Catherine Tierney is a sociologist, and she writes. She has a very nice book called The Social Roots of Risk. And she will argue that this bridge, if I extend her reasoning, this is independent, this is me, but I think she would argue that this is not unexpected, right? That somebody should have thought about this. The risk was always there. And socially, we decided we were not going to invest the money on protecting that bridge. So it is not a random natural catastrophe type thing. We created the catastrophe. And so that view, right, and again, I teach a little bit of that in my forensics class as an alternate point of view, is not what an engineer would think as, right? And so, there's another sociologist who's been around for a long time, Charles Sparrow, who is a professor at Yale, that basically argues that the reason we have more disasters is because we are putting more vulnerable infrastructure in vulnerable places. We build cities on the ocean or on rivers, and so if it floods, right?
Yeah.
So yeah. So again, it would be interesting to look at this disaster, not just in an engineering or economics, from an engineering and economics standpoint, but from a more holistic, to see what's coming up.
And you also mentioned, this is my last question, We kind of drove into the public needs to know about this type of stuff, and engineers need to be a part of it. How would you encourage engineers, or what steps could they take to be more involved in the public, besides maybe just going straight into politics? So there's some stepping stones. What do you suggest?
Yeah, there's got to be an intermediate place, right?
Well, I mean, just get involved locally, right? I mean, you start there with your city council, with local nonprofits and things like that. There are lots of ways of getting involved and lots of ways of making a difference at the local level. And then if you find it in you to go, regional or national, that's a different thing. But you do have the obligation, I would say, to do that, right? Engineers are supposed to take care of the health and welfare of the public. That's our mantra, right? And when you start thinking about it, it's almost on what I would call the mitigation side, in thinking ahead and preparing for, that we can be most effective. The more we do of that, the better prepared we will be for when something goes awry. And so I think that engineers need to do a lot more of that. I'm actually, our current crop of undergraduate students, I think, are thinking along the right lines for that. Engineering is a profession that changes very slowly, and for good reason. In other words, we have been pretty successfully. We have learned some pretty hard lessons along the way, right? And so we're not, most of us older people like myself, we're not willing to let the young ones just take over, right? We would like to do a transition, right? And so one of the things that I will also suggest to younger engineers is talk to some of the senior people in your company and get some of their wisdom. That it is very important that we do not lose that wisdom, because sometimes that happens in companies just because of the way that transitions happen, and sometimes the people at the middle leave, and you have some very young people and some very old people, and there's little or no communication between them, right? And so just become more involved, I think, is what it boils down to. And again, it's incumbent upon some of us in engineering education to provide the students with those tools. Again, communications being an important.
Yeah.
But I'm really upbeat. I'm very hopeful for the future of our profession.
Yeah, I like how you're talking so positively about the undergrads. It gets me excited for what's to come. So what you kind of touched on it a little bit about things that you would recommend, but we always like to ask our guests with the last question is sort of like what piece of advice you would give to younger engineers. I know you mentioned talk to the more experienced engineers and ones that have history and wisdom to share. It's definitely a big thing for our company. I know we have a lot of tenure, like people stay at my company for a really long time, and being able to pick their brain and like find out all of the details of like their 30, 40 years at the company, it really sheds a lot of light.
Okay. So my mantra will be travel and see the rest of the world, because the rest of the world does things differently. And we need to learn from them, even from countries that we consider less developed or anything like that, right? There are lessons to be learned there. I have been very lucky because I moved around quite a bit when I was young. And so I experienced different cultures. And so that has, I think, given me a broader perspective, on at least on some things. And so I think traveling is one thing, and read literature, good books. Some of the old good books, some of the latest books are also good, but just read and become acquainted with your culture and what makes the U.S. the U.S. I was born outside the U.S. I'm an American citizen, proud of it. I've been a citizen for about 50 years. And this is quite an extraordinary country. And so, but a lot of our students And it's not their fault. They just have not been educated in that. Don't have the historical perspective to understand just how unique our institutions are and how frail in some senses they are, right? And how we need to protect them. And so, regardless of what political views you have, you have to understand what are the frameworks that our culture has. And again, literature, art, music, all of those things are really important to round up the education of an engineer. But again, travel is the best.
I love that. I don't feel like we've had that suggested yet as the piece of advice. So I like that a lot.
Yeah, Roberto, thanks so much. It's been a pleasure having you on, and I really appreciate it.
That went a lot longer than I was supposed to.
Time flies by, so
yeah.
Right. I appreciate it.
I could talk. I'm a university professor. You give me time.
It was great.
I have lots of war stories.
Well, I loved hearing what you had to say. So yeah, thank you so much for joining us and shedding some light on everything that's going on in Baltimore. And it was great to talk to you. So thank you.
All right. Glad to do
thanks
it.
Again.
Have a great day.
Okay, yeah, you too. Take care.
Bye-bye.
I hope you enjoyed the episode today. We would love to hear your feedback, comments, and or questions. To leave them, please visit structuralengineeringchannel.com. There, you'll find a summary of the key points discussed in today's episodes, as well as a link to any of the resources or websites mentioned. Don't forget to subscribe to Apple Podcasts, Spotify, or wherever you listen to your podcasts. Until next time, we wish you the best in all of your structural engineering endeavors.